Hi everyone, welcome to the Seismic Data Processing course. This course from basic to advanced. We'll start simply by knowing the theory behind the seismic data, and then we will apply on real seismic data to enhance our seismic signal. What the seismic data? So the response of the seismic wave recorded at the surface of the Earth with respect to time is known as the seismic data. The seismic data help us to locate the groundwater, minerals in mines, to investigate location for landfalls, characterize how an area will shake during an earthquake, but the main use for seismic data in oil and gas, where we can detect the hydrocarbon accumulation. It also helps us to detect the subsurface geological features, the faults, especially fault joints and the dome. So the uses for seismic data and groundwater detections help us to detect the aquifers, for minerals in mine exploration used to locate minerals rich zone, landfall investigation, check whether an area is suitable or stable for waste disposal, earthquake analysis help estimate how much shaking might occur in area, and oil and gas to detect the hydrocarbon. So the elements of the seismic to record the seismic data, we have seismic source. This seismic source is generated by a vibrator on the surface or by explosion. So when the seismic wave goes through the layers of the earth, some of the seismic wave will bounce back when they hit the layers, and some will continue deeper. So when this seismic wave back to the surface, we have a geophones to record how much time it take for each wave to hit the layers and then back to the surface. From geophones, we have the data collection area, where all the geophones connected to the data collection area. Why seismic data processing? You can check the left image. We have a real image on Earth. So we need to when we get the seismic data, we are not getting the data immediately as the same as the left. We have the data have to go through processing to remove the noise and to enhance the signal. So that's why we will use two software to enhance our signal, and that's why we need the data processing. So we have land seismic recording and marine seismic recording. The same principles. We have the source to generate the seismic wave, and this wave will go through the rocks, and depend on the rock type. We have some of rock, we have sandstone, or this is clastic rock, and we have carbonate rock, limestone or dolomite, and shell. This is original to generate the hydrocarbon. And when these seismic wave go through the rocks, it will bounce back, and some of these waves will continue deeper. When it's bounced back, we have the geophone, and then go to the track, we're recording the seismic traces. For marine, we have survey ship, and we have the hydrophones. On the marine, we call them hydrophones. On the land, we call them geophones. Same principle. So when the seismic wave go through the rocks, and depend on the stiffness of this rock, we go from depth, we get at the end we get the time. But how we get that? So when the seismic wave go through the rocks, we have, for example, this one is shell and this one is limestone. So depend on the acoustic impedance. What is the acoustic impedance? It is how this rock it will resist the passing of the seismic wave. If the rock was very stiff, that means have very high acoustic impedance, and we will get the trace, we will get the reflection coefficient is very high, positive reflection coefficient. Acoustic impedance is equal to P multiplied by velocity. the P is the density multiplied by velocity. So if this rock have high density and high velocity, that means this rock is very dense. That means we will get very high reflection coefficient. That means we will get the trace in here, we will get positive trace. The trace will be from this side, positive trace. But if the rock was very soft, okay, low velocity, and this velocity for passing the seismic wave, and low density, we will get the reflection coefficient, we will get minus reflection coefficient. So this is 0, anything from here is positive, and we will get the value between -1 and +1, depend on the stiffness of the rock. So we get from depth into the time. So depend on the layers, we have shell, this is shell rock, sandstone rock, limestone, shell. This is depend on the acoustic impedance. If this rock have high acoustic impedance, we will get the reflection coefficient, we'll get positive reflection coefficient. So, and this is wavelength, so we have positive wavelength from this side. If the rock have low acoustic impedance, that means the velocity and the density is very low, we will get minus reflection coefficient, then we will get the trace from this side, from the minus. At the end, we will calculate the seismic trace, so we will get from depth into the seismic trace, and depend on the acoustic impedance. If the rock have very high acoustic impedance, that means this rock is stiff, this rock is, we will get positive reflection. Okay, so this is the key element of seismic trace. This is the seismic trace. There is a key element in seismic trace. We will describe them in more detail in the next lecture. So we have, this is the 0, anyone from the light is called, this is plurality hard, and anyone from the left, this is minus, it is for soft rock. We have high frequency, this is the cycle per second. We have very high cycles per second, this is for high frequency. And we have low frequency, the cycles per second is very low and wide, so this is low frequency. And also we have phases, 0 phase, 90 phase, and we have 180 phase. And also we have the wavelength is called by the velocity multiplied by the frequency, and we will describe that in more details in the next video. So this is, you can calculate the reflection coefficient, and you have the seismic trace. These are the layers, velocity, this is the velocity, this is the P, the density, the rho, 2.3 gram, we can for V2 is 2000, minus P1 is 2.2 gram per cubic centimeter, multiplied by V1 is 1500 meter per second. So when you subtract this one, the acoustic impedance 2 minus acoustic impedance 1, and then you add them, you will get the either is positive or negative reflection coefficient. And after that, we transfer the reflection coefficient into the seismic trace, because so how we get the time equal to 2d multiplied by the v. The time is the distance dividing by the velocity, so the distance in here is supposed to be multiplied by 2 because it's two-way down to the geophones, and multiply by velocity, you will have the time. So we go to from depth into the time. So this is all you need to know for the first lecture. We will continue deeper and deeper and deeper until we understand all the basic for seismic processing data, and then we will apply these processing on real field data SIG-Y to enhance our seismic traces. We have two software to do that. We'll use it in the next videos. So thank you for watching and see you in the next video.